Hello students, in this video we will see a miscellaneous problem related to geometric progression. Problem is if S be the sum of P the product and R the sum of reciprocal of n terms of a G. Prove that S upon R raised to the power n is equal to P square. As we know that the GP may be represented like this. First term is A, second AR square, second is AR, third one is AR square, fourth one AR cube, and so on up to AR raised to the power n minus 1. These all terms gives us an GP. So, according the given condition, S is the sum of these terms of all GP. So, S will equal to A plus AR plus AR square plus and so on up to AR raised to the power n minus 1. While using the properties of sum of n terms of GP, this S will equal to, first term is here A, common ratio is R raised to the power n minus 1 upon R minus 1. This is the sum. Now, see, second case, product, P represent for product. So, P may be written as P is equal to A into AR square and so on up to AR raised to the power n minus 1. See here we will have A how many times? N times. So the product of A up to n times will equal to A raised to the power n. Now see the product of R square and so on up to R raised to the power n minus 1 may be represented here 1 plus 2 plus 3 plus and so on up to plus n minus 1 terms. So this is A raised to the power n into this is R. Obviously 1 plus 2 plus 3 plus and so on up to plus n minus 1 represent an AP. This is an AP. So by using the sum of AP, we will get here S is equal to n minus 1 y2 y using the formula 2a plus n minus 1 into d and y2. When we will use this formula, then we will get S is equal to n minus 1 upon 2. So the sum of these may be written as R raised to the power n minus 1 y 2. This is the second relation. Now see the third case. R is the sum of reciprocals. So R may be written as 1 by A plus 1 by AR plus 1 upon AR square plus and so on plus 1 upon a r raised to the power n minus 1. This is also a GP. So I apply the GP formula. First term is a, that is 1 by a in the bracket. Common ratio is 1 by r. 1 by r raised to the power n minus 1 upon 1 by r minus 1. When we will solve this relation, we will have 1 by a, see properly here, r raised to the power n. Here we will have 1 minus r raised to the power n. In denominator, LCM is r, so 1 minus r. Okay. So this may be written as 1 upon a, 1 minus r raised to the power n upon 1 minus r into r upon r raised to the power n. See here again, this is 1 by a in this bracket, 1 minus r raised to the power n upon 1 minus r. This may be written as 1 upon r raised to the power n minus 1. Okay. Now see, this step very clearly here. This will equal to 1 by a. See this term. This may be written as r raised to the power n minus 1 upon r minus 1. This is again 1 upon r raised to the power n minus 1. This is the third relation. Now we will find SYR. As we have calculated S is a, r raised to the power n minus 1 upon r minus 1, and sum of these reciprocals, that is 1 by a, r raised to the power n minus 1 upon r minus 1 into 1 upon r raised to the power n minus 1. Now see the calculation here again. This will equal to a r raised to the power n minus 1 upon r minus 1 into a into r minus 1 upon r raised to the power n, r to n minus 1 into r raised to the power n minus 1. When we will simplify, we will get here a square into r raised to the power n minus 1. This term and this term we will divide it and say r minus 1, r minus 1. When we will do the product of this a to a, we will get a square, and this is r raised to the power n minus 1. So this is the value of SYR is equal to a square into r raised to the power n minus 1. Now see the next very important step. This way, s upon r raised to the power n is equal to a square into r raised to the power n minus 1 raised to the power n. Okay. So we will have here a raised to the power 2n into r raised to the power n minus 1. This step may be written as a raised to the power n into r raised to the power n minus 1 by 2 whole square. Okay. And this is the value of P. So finally you may write down S upon R raised to the power n is equal to P square. This we have to show. Okay.